Hello everyone, this is the second video on set theory. In this video I am gonna discuss about the types of the set, Venn diagram and some properties of the set. So before start the session, let us know about the cardinal number of the set. So cardinal number, if a set has n elements in it, then n is the cardinal number or order of the set. Basically the total number of elements in a particular set is cardinal number and it's denoted by n of a. For an example, let a equal to in tabular form WOLF. The total number of elements is n of a equals to 4. Now start with the types of sets. First one is singleton set. Okay, so if a set has only one element in it, then the set is called singleton set. We'll take some examples. Take a equals to 2. Okay, b equals to in set builder form x such that x belongs to n and x is between 2 and 4. Obviously there will be one number is 3. And the last one is x is a capital of India. X such that x is a capital of India, and that we all know that is Delhi. Okay, so it is also a singleton set. The number of a singleton set is 1. Now another type of set, most important, empty set or void set or null set. We all know what is empty means. If a set has no elements in it, then it called void set or null set or empty set. It is denoted by phi. It is a Greek alphabet. In roster form, the null set is denoted by empty space within second bracket. For some example, in set builder form, x such that x belongs to R and x square equals to -2, which is impossible because we all know that the square of a real number can't be negative. So in this example, the property of x, that is impossible. Therefore the set has no elements in it. Now the next example, x such that x belongs to n and between 1 and 2. We all know that between 1 and 2 there is no natural number, so it is also impossible. So this set also has no elements in it. Next example is x such that x is a prime number between 32 and 36, where 32 and 36 both are included. So between 32 and 36 there are natural numbers are 32, 33, 34, 35 and 36. Between of them they are all composite number, so this set also has no elements. So these three sets are examples of null set or empty set. Now the terms are finite set and infinite set. So what is finite set? If a set has finite number of elements in it, then it called finite set. Finite set also known as countable set. So let's take some examples in tabular form. Okay, so the first one is 1 2 3 4 5. It has 5 elements. And the second one, b x such that x is a vowels of English alphabet. We all know that it is A, E, I, O, U, right? This is also a finite set because it has only 5 elements, finite number of elements in it. Now the second one is infinite set. If a set has infinitely many elements in it and that is uncountable, that's called infinite elements. So we will take some examples. Let C be the set of all natural numbers that is written by 1, 2, 3, 4 up to infinite. This is also uncountable infinite set. Another D that is written in set builder form 1 by n such that n belongs to natural number, that is actually we can write in tabular form also 1 comma 1 by 2 comma 1 by 3 and so on. This is also an infinite set. And the most important, that is E in set builder form x such that x belongs to real, and this is between 2 and 4. So in this between number we have infinitely many elements, but remind it, we cannot write it in the tabular form. Okay, there are two types of infinite set also. One of them is denumerable. If the elements of an infinite set can be written in the form of sequence, then the set is called denumerable. In the previous example, the set C and set D both are denumerable. The second one is non-denumerable. In the other example, set E can never be written in the form of sequence or in the tabular form, cause x is the real number between 2 and 4 and there are infinitely many numbers between them. If there is no possible way to write the elements in the form of sequence, then the set is non-denumerable. Now let's talk about intervals. On the real line, various types of infinite sets are called intervals. There are many types of intervals. The first one is closed interval. Let's take some example. If a set is given by caps A, x such that x belongs to R and x is greater than equals to A and less than equals to B, then it can be denoted by A comma B within third bracket, and mind it, A should be in the left side and B in the right side. So if it is written as x belongs to A comma B within third bracket, it implies that x is greater than equals to A and less than equals to B. A is the minimum value and B is the maximum value of x. Another is open interval. If a set is given by B, x such that x belongs to R and x is greater than A and less than B, A and B both are not included, then it can be denoted as A comma B within first bracket, and this is not order pair. It means x is greater than A and less than B. Simple. Now last type of interval, that called semi-open or semi-closed interval. Let's take some examples. One is C, set C that equals to x such that x belongs to R and x is greater than A and less than equals to B. That could be written as first bracket A comma B third bracket. That means first bracket for only greater than and third bracket for less than equals to. Same like D, x such that x belongs to R and A greater than equals to x and less than B. Therefore it can be written as third bracket A comma B then first bracket. The third bracket is for equal to. Now let's do some problem sums. Write the following in sets as interval. Write down the sets given below. Now let's solve that question. Let's check the first question. X is greater than -4 and less than 6. There is no equal sign, that's why it is open interval, and write it as in the first bracket -4 comma 6. Second one is x is greater than equals to 2 and less than 7, that's why put for third bracket in the left side and first bracket in the right side. The third one is x is greater than -50 and less than equal to 30. That's why first bracket -50 comma 30, then closed it as third bracket. Okay. The last one is x is greater than equals to 5 and less than equals to 7. This is closed, that's why we put third bracket both side. Second question is write the following interval in the set builder form. Please note down the questions given below. Let's solve that question. Question number A, we can write it as within second bracket x such that x belongs to R and x is greater than -7, only greater than, as there is first bracket, and less than equal to 5 because there is second bracket in the 5. Okay, next question, x such that x belongs to R, x is greater than equals to 3 because there is third bracket, and less than equals to 10 also. This is closed interval. And the third one, x such that x belongs to R, x is greater than equals to 0 and less than 7. The fourth question, x such that x belongs to R and x is greater than -3 and less than 3, only less than, not equals to. Now see what is Venn diagram. Visual representation of a set is called Venn diagram. We can use any shape to represent a set and put the elements into the shape, like this or this or this circle, and put the elements in it. This is Venn diagram. Now the topic is subset. Let S be a set and T is another set, is said to be a subset of S if x belongs to T implies x belongs to S. This means that each element of T is a element of S also. So we write the symbol T, that symbol S, which is read as T is a subset of S or T contained in S. Let's take some examples given below. Write down the examples. Note that A and C both are equal. Their elements are arranged in different way, and D is another set. There are 4 sets given below. Okay, let's draw the Venn diagram. Okay, that's not a good idea. Let's eliminate this and draw a simple diagram. Look, the first one is, the first big circle is A, the upper one is D, and BCD into the big circle is set B, and another circle in green is C, because both sets are same. Now check the examples. Set B and set A. X belongs to B implies that X belongs to A. That means each element of B is a member of A also. Therefore, we can say that B is a subset of A and written as given below. Okay. So, but look in the other side. X belongs to A implies X doesn't belongs to B, as D and E are not in B. Actually, D and E not, it should be A and E. A and E are not in B. Thus, we have to write it as A, then the symbol, then cut it, then B. That means A is not a subset of B. In the other case, this can be written as below and read it as B is a proper subset of A. So, what is superset now? If B is a proper subset of A, we say that A contains B and A is a superset of B. Basically, if B is a proper subset of A is a superset of B. Equal set we have already discussed about. X belongs to C implies X belongs to A. That means each element of C is in A. Therefore, C is a subset of A. Also, we can see that each element of A is in this set C also. Therefore, we can say the opposite thing also. A is also a subset of C. Therefore, A and C both are equal. Note that this is very important to understand. If two sets are subsets of each other, then they are equal, and we will use this concept to prove many laws and sets equality. Now the last example, set D. Each element of D is not an element of A, therefore D is not a subset of A. Also each element of A is not an element of D. A is not also a subset of D. Neither A is a subset of D nor D is a subset of A. With those given examples, we can easily recognize which one is proper subset and which one is equal. Let's compare the symbol. This to this means less than or equal to. So if we write x less than equals to y, where x and y both are unknown to us, it means that x is less than y or x equals to y. And if we take some known numbers like 2 less than 3 or 2 equals to 2, there will not be any confusion. We can't write this as 2 less than equals to 3, as this can't be possible, and also 2 less than equals to 2. 2 can't be less than itself. Similarly, this subset symbol divided into two parts. If we write A is a subset of B, we can say that A is a proper subset of B, or A is a equal set to B. Now check out some special results on subsets. First one is every set is a subset of itself. The proof is given below. This is very simple to understand. And the second one is null set is a subset of every set. This is very important, and the proof is more important to understand. We will gonna prove this by contradiction. What is contradiction? In mathematics, we use this to prove some theory. In class 10, we already proved root 2 is an irrational number by contradiction. We know that root 2 is an irrational number, but we have to prove that by contradiction. That's why we have to assume that root 2 is a rational number. which is wrong. So there in the number system there are only two types of number. One is rational, another is irrational. If a number is not a rational, then it has to be a irrational number, right? So our aim is make my assumption wrong. So similarly, according to our proof, there are two cases. One is null set is not a subset of A, and another null set is a subset of A. These two cases are opposite. If case 1 is false, then case 2 has to be true. Our target is this. Okay, so let null set is not a subset of A, and just assume it true. Okay, we have to prove that our assumption is wrong. So if so, null set must have at least one element in it, which is not possible as null set has no element in it. So this is contradiction. Therefore our assumption means first case is totally false, then second case has to be true. Therefore null set is a subset of every set, and null set is called improper subset of A. The next topic is number of subset of a given set with cardinal number n. Let's take some set A which has 3 elements, that is 1 2 3. Cardinal number is 3. So there are 3 elements in it. If we select one element out of these 3 elements and put it in brackets, we will get 3 unique singleton proper subset of A, and they are this and this. Similarly, the subsets of A containing 2 elements out of 3 elements are 1, 2, 2, 3 and 1, 3. And the subset of A containing all elements, that is actual equal set, is 1, 2, 3 itself. So these are the proper subset. This is equal set, and we should not forget that null set is a subset of every set. This is improper subset. Total number of subset of this given set is 8. We can write this as 2 cube. So we have a formula: total number of subset of A with cardinal number n equals to 2 to the power n. Now let's prove that formula. To prove this theory, we should learn a brief concept about combination and binomial theorem. The concept of combination is the total number of selection of R different object, the total number of selection of R different object out of n different objects, and we write it as NCR. So when the cardinal number of A is n, that means A has n distinct element. Out of this, if we choose only one object, then it will become a singleton set, and the number of that is NC1, that is equal to n. Same as taking 2 elements out of n elements, we will get more different subset of order 2. Total number of that is NC2, and so on. Last one is taking all the elements together, we will get the equal set, and that is the number 1, and we can write it as NCN. Therefore the total number of subset, we can write it as NC1 plus NC2 plus NC3 NCN, and plus 1 for null set. Now we don't know how to solve it, that's why we will use binomial theorem. Binomial, the word you already know about. If a equation has only 2 terms in it, then it's called binomial. So let's take an example: x plus y whole to the power n. So when n equals to 0, it will become 1, and n equals to 1, it will become x plus y. N equals to 2, it will become x plus y whole square, equals to x square plus y square plus 2xy. We already know about this, and we already know how to solve x plus y whole cube, but we don't know how to solve x plus y whole to the power 4 or 5 and something else, something big number. So in this binomial theorem we will learn about this later. So now in this proof we will write some expansion, binomial expansion. So write down the expansion 1 plus x whole to the power n, that is equals to 1 plus nc1 into x plus nc2 into x square plus nc3 into x cube and up to ncn into x to the power n. When we put x equals to 1 both sides, we will get 1 plus 1, that is 2 to the power n, equals to 1 plus nc1 plus nc2 plus nc3 dot 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 ncn, and this is the total number of subset of A. This is 2 to the power n. So we will discuss about the family of set or set of set. If the elements of the set be sets themselves, then we will have a family of set and set of set. In this case, we will take an index set that is denoted by I, is a finite set written in the tabular form 1, 2, 3 up to n, and F be the family of n sets, that is A1, A2, A3 and An. Those are all individual sets. So F is expressed as in the tabular form A alpha caps A alpha such that alpha belongs to I. Now the power set, if S contains n elements, then the collection of all subset of S is a power set denoted as P of S. In the previously given example, we took A equals to 1, 2, 3. It has only 3 elements and it has total number of subset that is equal to 8. Put that subset together into a collection that is denoted by P of A. Next and the last topic is universal set. A set that contains all set in a given context is called universal set, denoted by caps U. That means a set that contains all sets under consideration, that is, it is a superset of each of the given set. We'll take some example. If A equals to 1, 2 and 3 in tabular form, and B is given below 2, 4, 6, 8, and C is 1, 3, 5, 7, and U is 1, 2, 3, 4, 5, 6, 7, 8. Basically the total elements of A, B and C, right? So in this Venn diagram we can see that the U is the superset of every set. A is also a proper subset of U, C is also a proper subset of U, B also a proper subset of U. Now we will see another Venn diagram, that is number system. Okay, so we can see that real number is the universal set because natural number is a proper subset of whole number is a proper subset of integers is a proper subset of rational number, but rational number and irrational number totally different set. Okay, but these two sets are also proper subset of real number, therefore real number is the superset of this every set. So this is an example of universal set. So this is it. This is set theory lesson 2. We will talk about the union, intersection, difference, symmetric difference in session 3.